Hi everyone, my name's Sam. I'm a postdoc at the University of Manchester, and I'm going to present in today some work I did during my PhD looking at iron and magnesium diffusion of olivine crystals in Polar 15 Mare basalts. So a bit of background into the Polar 15 Mare basalt samples. They're low titanium and they were erupted approximately 3.35 to 3.25 billion years ago. And when they looked at the samples that they'd collected and examined the bulk rock chemistries, they could see that they could divide the samples into two suites. And these were known as the olivine normative suite, which will be shown in green for this presentation, and the quartz normative suite, which is in blue for the remainder of the presentation. And naturally, one of the first questions that then came about was, how do we get these two suites with different bulk chemistries at the same landing site, and what's the origins, what's the petrogenetic relationship between these two suites? So currently, based on some trace data work, there's sort of two different competing theories. The first, shown in the center here, is that we have similar magmatic histories between the two suites, but potentially a difference in source composition that's led to the differences in chemistries between the two suites. Now, the other hypothesis is that actually we have a similar source for both suites, but the difference has come about due to differences in magmatic history, namely that the quartz normative basalts experienced a more complex magmatic history of multiple fractionation events within the lunar crust, and this led to a difference in chemistry compared to the olivine normative basalts. So where the diffusion work comes in is that we're trying to see if that we can get any evidence from diffusion timescales to potentially suggest that olivine crystals in the quartz normative basalts might have experienced a residence within the crust, within some of these potential lunar magma chambers prior to their eruption, that might give out longer timescales, longer diffusion timescales compared to the olivine normative basalts. And in turn, this would give us some indication about which of these two competing hypotheses about the origins of the two suites is more likely. So to do that, we looked at olivine crystals from 9 different Apollo samples. In total, we identified 48 crystals of interest that showed grayscale profiles and image data that were indicative of diffusion. And then we took these samples, analysed them using the SEM to get backscatter maps and for calibration for the probe data. So we got the crystal compositions from core to rim for each of the crystals. And we also got orientational data with EBSD to correct for crystallographic orientation within our models. And then the variables that we required for the diffusion modelling were temperature, which we got from some MELTS modelling, oxygen fugacity and pressure. These were taken from literature values for lunar magmatic systems. And then we also had to input a crystal growth rate and a cooling rate, and these were taken, these were the variables that we changed to try and get the best fit for our models. So as mentioned just then, we had crystal growth and cooling rate input into our models. Now, this is different to some of the initial models we tried. So we initially used an isothermal model with a set temperature, and this is shown in yellow on this plot here, where we've taken an example traverse across the crystal shown on the left here. And as you can see, the yellow modelled trend is offset slightly from our open circle EPMA data points in the core and in the rim. And we found this with a lot of the isothermal model runs that we ran. So instead we switched to a dynamic diffusion model, and this then takes into account the effects of crystal growth and changes in boundary condition as the model proceeds, and these are shown in black on this graph here, and as you can see, it's visibly a much better fit to our EPMA data than the isothermal model was. So we proceeded with the dynamic diffusion model, and this is our results in terms of plotted up some diffusion timescales against the different different samples, and each crystal within each sample. So each X on this graph here represents a different crystal, and the field shown in green is sort of the range for that individual sample. So we managed to fit profiles for 29 olivine crystals, 22 from the olivine normative samples, and unsurprisingly, we only managed to get 7 profiles from olivine in the quartz normative samples. As we can see from here, in blue, here's our quartz normative samples and crystals, and we got a timescale range of 5 to 24 days from these. And then on the right here is the in green the olivine normative diffusion timescales, and these range from 6 to 91 days. In general, the timescales between the two suites are quite comparable. Like, they suggest that they've got similar thermal histories. We're talking similar ranges, in timescales from several days up to a couple of months. We're not talking one suite has a range of days, the other suite has a range of tens or hundreds of years. And in terms of what these diffusion timescales are showing in general, they're relatively short, so it's likely dominated by growth, and the diffusion is taking place during cooling within a lab flow, as opposed to a setting in sort of a crustal magma chamber type setting where they would be allowing longer diffusion timescales. So in summary, our results, I'd say, they've shown similarities between the two suites, likely experience similar thermal histories, and this is likely to have been in a lab or on the lunar surface. In terms of estimates of lava flow thicknesses, this is also something that we calculate but didn't have time to go into here, but it's really useful in terms of looking at magmatic flux through time on the moon. And linking back then to what was shown in the introductory slide, with these two competing models, our data suggests that actually we're looking at a situation that's more favourable, where we've got similar magmatic histories, and therefore it must be a difference in source and magma source that's resulting in the chemistry differences between the Apollo 15 Mare basalt suites. So I'll leave it there and welcome any questions.